Alright, for this video we're going to talk about the difference between continuous and discontinuous functions. And really the main thing is are the x values connected all the way through? Are there any sections that are disconnected, any holes that are missing? But essentially what we're going to be looking at is for a continuous function, we want it to be connected all the way through from wherever it starts to wherever it stops. There's no pieces that are missing. So it's a function whose graph does not have any holes or any gaps. So when I say holes, that means an x value that's missing, or gaps means that it jumps up or down, or there's any sections of the x that are missing. Okay, so it's kind of like if I put my pen on the graph and I'm able to trace all the way through it without any disconnect, that means that it is continuous for all x values. You can also have a continuous function that has endpoints as long as there's no x's in between those two values that are missing. So it doesn't necessarily have to have arrows on either side. It can have endpoints as long as everything in between is all the x values are included. Now we're going to talk about the types of discontinuous, which you're going to need to identify these. I have separated the removable type into two different, I guess type 1 and type 2. They're not necessarily called that, but just to kind of give you the difference in what you're looking at. So it says it is a function that is removable whose graph has a disconnected point that is defined at another value. Okay, so what that means in this particular problem is when I'm looking at a graph, I'm tracing over it, and I see that I have a hole. I call it a pothole right there. Now, that hole means that on the graph itself, there is a x value that is missing. However, if I look above and I go above that x value, I can see that there is an x value, but it's part of another graph. Okay, so there is an x value, but it's on another y value in that problem. Now, the reason these are two separate things is technically I have an x value. Like if I say I'm including all the x values from infinity to a negative infinity, I can say that I have an x value here. But in the graph itself, the graph has a hole. Even though there is an x value up here on another part, there is a hole here which makes it discontinuous. It's not one continuous piece. It's not one continuous roller coaster. Okay, this hole right here is a disconnected piece. Even though there is an x value and it is defined, that does not make it part of this graph, which means the function itself is discontinuous. Okay, now we also have what we call removable part 2. Now, I call it removable type 2. When you do your assignments, they're probably just going to call both of them removable. Now, the removable type 2 is because I still have a missing hole. Okay, so I have a pothole, but the function where it is disconnected is undefined at that x value, which basically means that at that x value, there is no other x value above it or below it that fills it in. So that x value is just not included. So right here, we're just going to say that x does not equal whatever that value is. They're calling it a, it could be whatever number. Here, I know that even though it's disconnected, that my x value does still equal the a value that we're looking at because the x is still included. However, over here, there's nothing to fill in that pothole. Okay, there's both still removable. So remember, removable discontinuity means a removable point. There is a one point or one x value are missing from the graph. Okay, now we also have what we call jump discontinuity. So jump is just that. It jumps up, kind of the y values are missing this time. So it's not one continuous piece. So it's like we're going, but we can't get from this piece to this piece unless we jump up. Or In some other situation, we may have to jump down. So the function whose graph has ends that do not connect. So these have ends that are not going to connect. And so I'm going to put missing y values, because there is a section of y values that are going to be missing if you're jumping up. Now, this may be super old school and you may not even know what I'm talking about, but there used to be this Donkey Kong game. It was like the original Donkey Kong, where one of the games you actually had to ride a cart in one of the mine things. And in order to ride the cart, there were disconnects in the track. So as they're riding the track, you had to be able to correctly hit the button to jump to the new track to keep going. So I always think about that mine cart. I don't know if you want to look it up with the Donkey Kong game and the mine track, but you're riding on the track, but in order to keep riding and not fall off, you've got to jump up to get to the new track and keep going. Okay, so jump discontinuity means it's disconnected and there's missing y values vertically. All right, and the other type that we're going to talk about is infinite discontinuity. Now, infinite comes from the word infinity, which means that the graphs are disconnected, but they're disconnected not with endpoints. They're still going to have sections that are going to go to positive infinity or negative infinity, but they're never going to come together with each other. So when I'm looking at this one, it's a function where one or both sides of a section of a graph go towards infinity. And of course, that is going to include negative as well. Okay, so it can be positive or negative when it comes to these infinities. Now, I'm not sure how many of y'all remember or talked about this in Math 2, but when we have infinities like this, so if you notice, I'm going along my track, this one's going to keep going to infinity. This one and this one are never going to connect because this one's coming from infinity and it's going down. Now, these are disconnected in here, and that type of disconnected discontinuity for infinity is actually called an asymptote. We are going to be talking about asymptotes a lot. Okay, so an asymptote is an invisible fence. And that invisible fence is an x value that is not included. So it's like they're going, think about a wave going towards a wall. So if a wave is going towards a wall, it's going to hit the wall and it's going to bounce off of it, but it's going to keep going down the wall. So again, if we're going towards the wall, we're going to keep going down the wall, but we're never going to actually go across the wall. So a asymptote is an x value that the graph will never be equal to, and it's an invisible line where the graph is going to approach that value like a wall, and it's just going to keep going towards it, but never actually get and approach that value. It's going to get as close as possible. And it's called infinite discontinuity because it's approaching it, but never actually, and it's going to keep going to infinity along that wall as long as it continues. Okay, so again, we have three types. We have removable. Removable means I got a hole. I can have one where the hole is completely gone and nothing, and no other x value fills it in. Or I can have the type where I do have another x value that fills in, but the graph itself does have a missing removable hole. Jump discontinuity means that we're going along, and in order to get to the next part, I've got to jump up or jump down to get to it. Infinite means that the pieces are disconnected and they're going to infinitely go, they're never going to actually connect to each other, but they're going to infinitely go to positive infinity or negative infinity. They're just going to keep going and keep going. Most of the time that is happening because there is some type of asymptote, and that asymptote is that invisible fence that is going to be approaching. So we have this graph over here, and we have a domain that goes from -7 to 7. So we're looking in between here. We're going to identify all the types of discontinuity. So when I look at my discontinuity, I have this first one. I have a disconnection right here. Okay, now I don't know what else may be going on in other parts of the graph, but I have a hole. Now, technically, at the end, it can be a little iffy just because ends are a little bit different when it comes to what should be in between. But for right now, we're just going to say there may be some other parts to this graph that we're not seeing. And we're going to say that at x equals -7, we have a removable discontinuity. My x in the graph itself is missing, and technically I can fill it in, but it's still removable. All right, as we keep going to the next part, we can see that we at -3, we have another hole happening. Now, that one does not fill in, so at -3, yes, -3. So at x equals -3, it is still removable. It's just that that one doesn't have any other x value that fills it in. So when you do your practice today on Delta Math, they're going to ask you to look between, let's say, -7 to 7 and tell me all the x values that have discontinuity. So right now, my x values that have discontinuity are -7, it's removable, -3, that's removable. All right, I keep going, so I'm going along my graph. There's a hole there. There was technically a removed section there. And then we have this jump here. So why is this a jump? So right here, I would have to fill it in, or there's a hole in the graph and there's stuff on both sides. But here, I've got to physically jump, and there's some vertical section that is missing. So when I have to jump from one part to the other, that is the jump discontinuity. So for that section, I would be able to say that at x equals 2, that is going to be jump discontinuity. Okay. And again, I don't know if you even know what I'm talking about, but the Donkey Kong game where you're riding along the train track in the mine, well, technically you're not at the hole because you'd have to jump over the hole, but you're riding along and you would have to jump from one track to the next to keep going. All right, and the last point of last discontinuity that I see is going to be infinite discontinuity. So if you notice right here, these two sections are disconnected. Now, when you look at graphs on like the calculator or anything like that, they're not going to show you the asymptotes. What you're going to have to look for is when it's going infinitely off in one direction, it's kind of leveling out like a vertical line. When it levels out like a vertical line, that means that there's an asymptote there. And because of that asymptote, we have infinite discontinuity. So that's happening at x equals 4. And these are actually going in opposite directions. They don't always have to go in opposite directions. They can go in the same direction. It's just that they would be on different sides of that invisible line. But this is going to be infinite discontinuity because it's going off infinitely in the positive or negative direction. All right, now, when I get to the end down here, this point is just included. There's no holes. There's no other pieces that fill it in, so we're not going to call that discontinuity. Because we can have, once again, we can have endpoints when it comes to graphs that are continuous, but everything in between would have to be included to be continuous. And that's the reason we kind of looked at that one, because it was open, but then we had another value that filled it in.